Welcome to Lecture 38, in which we're going to be alternating between very profound and very applied applications of magnetism in relation to electricity. Now that you understand how moving electric charge is the source of magnetism, and subsequently you understand Faraday's law, the principle of electromagnetic induction, that changing magnetic fields gives rise to electric fields, we're ready to look at an interesting thing that happens in all circuits, particularly in circuits that are designed with lots and lots of coils of wire to make this phenomenon happen. Let me begin by looking at this wire loop. This could be a model of any electric circuit. So what I'm going to describe would happen in any electric circuit, but this is basically the simplest one I could imagine. So suppose there's no current in this circuit, and then I want to start a current flowing around the wire loop. Well, what happens? As soon as I start a current flowing, there is associated with that current a magnetic field, because moving electric charge is the source of magnetic fields. The magnetic field lines wrap around the wire that's carrying the current, and in particular, the magnetic field lines penetrate through the area bounded by this circuit. So there's a magnetic flux through this circuit caused by the circuit's own magnetic field, caused by the current that's flowing in that circuit. But we know that changing magnetic flux creates electric fields, and those electric fields oppose the change that's giving rise to them. So if I'm trying to build up the current in this loop, starting at zero, as soon as I try to change the current, I create a changing magnetic flux in this circuit itself. And that changing flux is going to oppose the change that gave rise to it, namely the buildup of current. And the net result is it becomes difficult to build up currents in circuits. That property of all circuits is called self-inductance. It's most important in circuits that enclose a lot of their own magnetic flux, and that is typically circuits that are coils and coils of many turns of wire. But in principle, it's there in every circuit, and when you're working with very high-frequency circuits, for example, in computers or radar or televisions, things like that, it can be a very important property, and it can sometimes be a nuisance. Let's look a little bit more about where this self-inductance comes from. So, again, a picture of a loop similar to the one I was just showing you, and we want to ask what happens as we try to build up current in that loop. So the current creates a magnetic field in this wire loop, and it would do so in any circuit whatsoever. That self-field results in magnetic flux through the loop itself. The change in the current changes the magnetic field and changes the magnetic flux, so we have a changing magnetic flux. Changing magnetic flux, we know, induces an electric field in the loop. There's the electric field, and the direction of that electric field is such as to oppose the change in current. That's the phenomenon of self-inductance. And we now want to quantify that phenomenon because we're going to use it both for practical applications and also to understand something very profound about energy in magnetic fields. So that's why we want to look at this phenomenon of self-inductance. So here again is my loop. This time I've shown you the loop area and I've indicated the magnetic flux phi, capital Greek phi for magnetic flux, through that area. We define the self-inductance as the ratio of the flux to the current. So if a circuit encloses a certain amount of its own magnetic flux, the ratio of flux to current defines the self-inductance. The more current, the more magnetic field, and the more flux. And so that ratio doesn't depend on either the flux or the current. It's their ratio. But what it does depend on is the geometrical configuration of whatever that circuit is. In this case, my simple one-turn loop. The unit of flux is the Tesla meter squared. That's B times A, flux per ampere, per current, and that's given it a name Henry, after the American scientist Henry, who was a 19th century scientist who studied electricity and magnetism. So we can also write that the flux, just inverting this definition, multiplying through by I, the flux is the self-inductance, this property of the circuit that talks about how much of its own flux it encircles, times the electric current that's flowing in that circuit. Now, we're interested in rates of change of magnetic flux because we know that the rate of change of magnetic flux is what gives rise to induced effects. So if I take the rate of change of both sides of that equation, I have on the left delta phi over delta t, the rate of change of magnetic flux. The inductance L is a property of this circuit itself. That doesn't change, and so the only thing that can change the right-hand side is a change in current. So delta phi over delta t, the rate of change of magnetic flux, is this inductance times the rate of change of the current in this circuit. And a device, by the way, that's specifically designed to have a lot of inductance or a particular value of this inductance, typically a coil of wire, is called an inductor. But we understand from Faraday's law, from the principle of electromagnetic induction, that the induced voltage is minus the rate of change of the magnetic flux. So now I'm going to put together these two things, electromagnetic induction and this definition of self-inductance, and I find that there is a voltage across the inductor, call it V sub L, and it's given by Faraday's law minus the rate of change of magnetic flux, but we found the rate of change of magnetic flux was the inductance times the rate of change of current. So there's a voltage across an inductor which is related not to the current through it, as in a resistor, but to the rate of change of the current. And it's got this minus L delta I delta T. So let me look at this equation in a little bit more detail. Here it is. The inductor voltage is minus the inductance, this property of the circuit, times the rate of change of current. And on the right, I've shown you the symbol for an inductor. It looks like a coil of wire because practical inductors, as I've said, are in fact coils of wire. And I've marked the voltage across the inductor, and I've marked the current through the inductor, in this case flowing downward. And the voltage is defined to be positive if it increases as you go in the direction of the current. So that's why the plus and minus signs are marked there on VL, as I've shown. In fact, it could well be the case that, for instance, if the current in this inductor were flowing in that direction but were increasing, then delta I over delta T would be positive. L is a positive number. That minus sign would make the voltage across the inductor negative, and that means the signs that you see there would actually be reversed. The voltage would be higher at the top because the inductor is trying to push back on the circuit that's trying to increase the current and make it more difficult to increase that current. So there's the voltage across the inductor, the inductance, and the rate of change of current. And there again is that special minus sign that ultimately is all about conservation of energy, as we've seen with the cranking of the electric generator and many other examples. So there's the anatomy of the equation that describes inductor voltage. The consequence of all this is the current through an inductor can't change instantaneously. It's hard to build up the current, and it's also difficult to stop the current in the sense that it simply will not stop flowing instantaneously. If it did, there'd be an infinite delta I over delta T and an infinite voltage, and that's impossible. But that leads to an interesting situation that can actually be dangerous. Suppose I consider a circuit in which I've got a battery with its voltage VB there. I've got a switch, I've got a resistor, I've got an inductor. Let's look at the dangerous situation first, then we'll come back and look at the less dangerous situation. If that switch is closed and I wait a while, a current I will gradually build up in that circuit flowing around, as I've suggested here, in the clockwise direction. What happens if I suddenly open that switch? Well, that tries to interrupt that current instantaneously. That can't happen. The current tries to keep flowing, and it will do whatever it can to keep flowing, at least for a brief instant. It will typically, in opening that switch, cause a big spark to fly across that switch. It will build up a very large delta I over delta T, a very rapid change in current, and that will cause there to be a very large voltage. That could be a small battery. VB there could be 6 volts, for example. Nothing that would hurt you. And yet people have actually been electrocuted, opening switches in circuits that have large inductance. Let me do a demonstration of that. Over here, I have indeed a 6-volt battery. Can't hurt me. I have a switch, which is just a metal piece that can make contacts to close a circuit. I have an inductor. This is 1/2 of that transformer I showed you in an earlier lecture. And it's just a coil of wire, and to make its inductance bigger, to concentrate its magnetic flux, it's mounted on this iron core. That just increases the inductance. And I have connected across the inductor this light bulb. It's a light bulb that takes about 6 volts or a little more to glow to full brightness. So I'm going to close the switch. And the light bulb is glowing, and it's bright but not super duper bright. Now I'm going to open the switch. Now this is the dangerous situation, but I know that this inductance is not big enough that it's going to electrocute me. But I want you to focus on what happens with that light. This is the light lit as it would be, or as it is, when it's connected across this battery. That's the best this battery can do to that light bulb, the brightest it can make it. I'm going to open the switch. And you see the light bulb flash instantaneously as I open the switch. Where did that extra voltage and current come from? It came from the inductor. It came from the collapse of the magnetic field and the induced voltage that occurs as a result of that. And that's what could, in fact, be dangerous in some situations. Let me do it once more. The switch is closed. I let the current build up for a little while. bang, I open the switch, and there is that bright flash. And with bigger inductance, even with still 6 volts, and with more current flowing, that could have been really dangerous. We would have seen a big arc across that switch. It can do damage. It can literally electrocute people. Let's talk a little bit more about what happens in this circuit and the other side of things when I first close the switch. Because when I first close the switch, there's initially no current flowing, and the current can't change instantaneously, so it takes a while for the current to build up. And I'm not going to work out all the mathematical details of this, but the current in that circuit builds up gradually in a curve that gradually levels off. And that should remind you of something. It should remind you of the picture we saw on the oscilloscope when we charged a capacitor through a resistor. And here is the beginning of a wonderful complementarity, ultimately between electricity and magnetism, in this case between inductors and capacitors. In a capacitor, the voltage builds up in that with that characteristic curve, and you'll remember there was a characteristic time which we got by multiplying the resistance by the capacitance. Here, the current builds up with a characteristic time, and that characteristic time turns out to be the inductance divided by the resistance, L over R. So there's a characteristic time, and I've plotted on the bottom axis there of that buildup curve the time in characteristic times. In the case of this circuit, the characteristic time is very short, so the light bulb essentially comes on to your eye immediately. But it really is taking some time as determined by this inductor and the resistance in the circuit, which is also, in this case, just the resistance of the wire in here. So that is the electrical property we call inductance. And it's an important thing in electric circuits. It's used in a lot of practical applications, but it's going to lead us to a more profound understanding of electromagnetism and magnetic energy. And as we move on to that, let's take a quick look at how magnetic energy might build up in an inductor. So here I'm going to plot a graph of the current in an inductor versus time. And I'm going to imagine that somehow I build up current at a steady rate. Now, that wouldn't happen in a simple circuit with a power source like a battery and a resistance. That would build up with this kind of exponential charging curve. So I would have to do some fancy electronics to keep pushing current at a steady rate against that back voltage that is trying to oppose it. So let's just assume I've built a piece of electronics, and my students in my electronics course could figure out how to do this, that will cause delta I over delta T to be a steady current, or building up at a steady rate, and consequently the rate is going to be the final current divided by the time it takes to do that. So here's the current building up, and we reach some final current I at some final time T. There they are, I and T. And so the rate of change, because it's steady, is simply I over T. I'm doing that because it's going to help us to solve this problem without having to resort to calculus. We wouldn't have to make that assumption if we used calculus. So the inductor voltage we know has magnitude. Again, I've put the absolute value signs because I'm not going to talk about the minus sign. The inductance times the rate of change of current, as we've seen. The power in any electrical situation is the product of the current and the voltage. So there's the current, there's the voltage, multiply them together. The average current during this buildup is half the final current. So the average power, which I designate with that bar over the P, is half IV, which is a half IL delta I over delta T. But remember, with this steady buildup, delta I over delta T is the same as the final current over time. So there it is. So now let's ask how much energy got put into this inductor. Because energy did go in the inductor, and it got stored in the inductor, and we'll see soon where it got stored. That quantity works out to 1/2 Li squared. I got two i's there, so they're squared, divided by T. Power is energy per time, so the energy that gets stored in the inductor is the power times the time. So that's that average power times that time, and that's 1/2 Li squared. So the power stored in the inductor, the energy that got delivered to the inductor, is a 1/2 Li squared, a result that we'll use with profound results when we look at how energy is stored ultimately in magnetic fields. Before we do that, we have to move into the practical world for a minute and look at a particular kind of inductor that will be easy to understand. So let me introduce you to something called the solenoid. And a solenoid is nothing but a long coil of wire. Here I've got a solenoid. It's a coil of wire. It's wound on some kind of hollow core. It could also have something in it like metal, but this solenoid is an air core solenoid. It's hollow. And I've shown a picture on the right here where you see a single loop of wire and then several loops and then more loops and finally at the bottom quite a few loops. And when a solenoid gets very long compared to its diameter, the bottommost picture suggests, it develops a magnetic field inside it which is essentially uniform and quite strong, and the field outside is rather weak as those field lines have to converge around on themselves to make that dipole-like looping of the field. Let's take a look at what the field of a solenoid looks like. Here you actually see a solenoid with iron filings around it, and I'm going to do the same thing with a demonstration over here in which I've got a very loosely wound solenoid, these green wires, and I've got a lot of little compasses under them, and the compasses are pointing sort of northish. Again, in the laboratory with all the metal around, it's hard to get them exactly right, but they're all pointing in some direction, and I'm going to turn on a pretty hefty current, about 7 or 8 amps, and watch what happens to those magnets. There they go. And you can see the ones in the middle are all lining up. These are not liquid-filled magnets, so they take a while to damp their motion out. But there they are. The ones in the middle are all lined up, showing that strong, uniform field. And the ones on the end are at least giving a hint that field lines are curving out, which they are. And in fact, they're going around in big loops like that. But the field outside is very weak, and the field inside is quite strong. And that's the property of a solenoid that's going to be of interest to us. It essentially creates a uniform magnetic field in its interior and a very weak magnetic field outside. That should sound similar to something you know about capacitors, which create essentially uniform electric fields in their interiors and rather weak fields outside. Let's do one more thing with our solenoid. This time I'm going to connect the big real solenoid to the same source of power, about 7 amps flowing through it, and I'm going to take this wrench and hold it right here. And the wrench is pulled into the solenoid because it experiences a magnetic force. The individual little magnetic dipoles in the iron of the wrench experience a magnetic force in the non-uniform field at the entrance to the solenoid. Once they're inside the solenoid, it doesn't experience any net magnetic force, although it is tended to align horizontally along the axis of the solenoid. It gets hard to pull it out, and if I hold it there again, it gets pulled back in. So that's a solenoid. And we're going to use solenoids for both practical and profound applications. Solenoid, again, a long, tightly wound coil. Let's get a little quantitative about it. It has N turns per meter of length, I'm going to say, and it's carrying a current I, and I will not derive this, although it's not difficult to do so. Inside, there's a uniform magnetic field given simply by the product of the number of turns per unit length and the current. And you can see why the current, of course, makes more magnetic field than the number of turns. Each one gives more flux, so there's more magnetic field, and of course the magnetic constant is going to play a role in there. There it is. There's a much smaller field outside. As the solenoid becomes infinitely long, the outside field becomes 0, and the inside field becomes perfectly uniform. It becomes like the field of a bar magnet for a long solenoid. Way, way far away, it looks like the field of a dipole, as does the field of virtually any circuit. Let's be a little bit practical about solenoids. One place they're used is in MRI scanners. If you've had an MRI scan, you've been inside a very big solenoid. They are used to create straight-line motion in electromechanical systems. When you turn the key on your car to start your car, what you're doing is, first of all, engaging current to a solenoid. The solenoid pulls a plunger in, just like my solenoid pulled in that wrench, and that plunger does two things. It's a switch that makes a connection that carries the hundreds of amperes to the starter motor, and it also moves a little gear out that engages a gear from the starter motor onto the engine. So the starter of the car has a thing called a solenoid, and that has to work first to get the starter motor going and engaging with the engine of the car so it can start the engine. Another very mundane application is electrically actuated fluid valves. When you press the button to start your dishwasher or washing machine, the first thing that happens is a solenoid valve opens, and a little plunger pulls, and that pulls a diaphragm and lets the fluid go flowing through. This picture is of a washing machine valve. So solenoids have a variety of realistic applications. And let me do a little calculation here to show you what can happen with solenoids. This is an actual disastrous situation. It's a disaster that has occurred. I'm not going to try to scare you away from having MRIs because it is very, very, very rare. But anytime you have superconducting magnets, and we use superconductors, remember those are materials with no electrical resistance, we use them in MRI solenoids and a lot of other applications where we want big magnetic fields without much power because it doesn't take any power, electrical power, to run this thing. So this one's going to have an inductance of 1 Henry, a current of 2,000 amps is flowing, it loses its liquid helium and the superconductivity ceases, and these things have copper and silver wires embedded in them, and so there is a small but non-zero resistance, and I want to ask how much energy has to be dissipated. Well, the energy stored in a solenoid is a half Li squared, as we saw. That's a half times 1 Henry times 2,000 squared. 2,000 squared is 4 million. The half makes it 2 million. 2 million joules of energy we got to get rid of. What's the initial power? It's I squared R. 2,000 squared is 4 million. It's a quarter of an ohm. That gives me 2,000 squared, quarter of an ohm, 1 million watts. We got to dissipate. That's like 10,000 100-watt light bulbs burning simultaneously. And we got to make that power go away. We got to dissipate that energy. For how long? Well, the current and drops down with this characteristic time L over R. In that case, it's 1 Henry times quarter of an ohm. So that divided by a quarter of an ohm. So that's about 4 seconds is the characteristic time during which this crisis occurs. And there's a picture of an MRI solenoid losing its helium coolant, big cloud of condensed air, condensed water vapor forming. You may have heard of the disaster that occurred when the Large Hadron Collider, the big particle accelerator on the Swiss-French border, was first turned on, and there was a bad connection, and there was this kind of process, a quench. They lost superconductivity, and they lost a lot of liquid helium, and it was a big disaster that shut the thing down for a couple of years. So that is a problem that can happen. So let's move on now and take this solenoid idea and go deeper with it now into what's really profound about all this, and that is magnetic energy. Before we get there, I have to motivate the inductance of a solenoid. So a solenoid is going to have length L, and I'm using this script L so I don't confuse it with the L for inductance. It's got a cross-sectional area A. It's got N turns per meter of length. Here's a picture of it. It's carrying a current I. The magnetic field, as we saw, is mu naught times N times I. The flux is therefore BA mu naught times N times I through each turn, but it has a total of N turns, big N, where N is little n, the number of turns per unit length, times its length. Put that all together, you get a total flux. Divide by the current, and you get the inductance. That's the definition of inductance, flux per current. So we've calculated quickly the inductance of a solenoid, and now we want to find the energy that's stored in that solenoid. The energy in any inductor we saw quite rigorously on the big screen is a half times its inductance times the square of its current. Let's work that out for the case of our solenoid. The inductance of the solenoid is mu naught N squared A L. The magnetic field is mu naught N times the current. The solenoid carries energy U, the stored energy in the solenoid, a half times its inductance times the square of its current, a half N mu naught N squared A L times I squared. So there's the energy stored in our solenoid. And I'd like to work on that just a little bit. There is a slight rearrangement of that, just algebraically rearranging it. I've got AL, I've got 1 over 2 mu naught, and I've got mu naught N I squared, all squared. So there's the N squared, there's the I squared, there's the mu naught in the upper quantity squared, but the mu naught downstairs that I've added takes care of it. I put it in that form because you'll notice that that quantity, mu naught times N times I, is in fact the magnetic field. So I can rewrite this expression as 1 over 2 mu naught B squared times the area of the solenoid times the length of the solenoid. Now this is a lot of math. Sometimes when I'm teaching physics, I'll give what's called a math alert before this because there's kind of going to be some heavy math to slog through, but it's going to lead us to a really profound conclusion, and now we're almost at that conclusion. So let's take a look at that expression. We found the energy stored in the solenoid. It's this expression involving a factor of a half, the magnetic constant, the square of the magnetic field. This haze should begin to sound familiar, and this product of the area and the length. That's the solenoid's volume. Area times length is volume. So what do we have? We have the magnetic energy density, the energy per unit volume stored in that solenoid. And where is it stored? It's stored in the one thing that is there in the solenoid when there is current flowing that isn't there when there's not current flowing. And what's that thing? That thing is magnetic field. So we have energy stored in the magnetic field of the solenoid, and the total energy is the energy density times the solenoid's volume. And I'm going to make the same leap of faith that, again, in a more advanced electromagnetism course using vector calculus, we would prove this rigorously. It is, in fact, the case that this is not only true for a solenoid, but it's true anytime we have a magnetic field anywhere in the universe. That magnetic field represents stored energy, and the density of that stored energy scales like the square of the magnetic field, just like we found earlier that the density of electric energy scales as the square of the electric field, and we've got that half, and we've got the magnetic constant in this case instead of the electric constant. So now we have expressions for both electric and magnetic energy densities. Let me talk a little bit about the practical and profound aspects of this magnetic energy storage. So wherever there's a magnetic field, there's stored energy, and it has energy density given by this symbol lowercase u sub b, the lowercase u for energy density, and that's equal to 1 over 2, 1/2, a constant, the magnetic constant mu naught downstairs, times the square of the magnetic field. The energy density is 1 over 2 mu naught b squared. That's the magnetic energy density. Where does that occur? It occurs in any circuit with inductance. And I've got a picture up here showing an automobile ignition system. When your car runs, the sparks that spark the spark plugs to light the gasoline, in fact, come from the collapse of magnetic energy stored in the ignition coil. The ignition coil of your car is a device that builds up electric current. In the old days, it was mechanical points that opened and interrupted that current, just like I did with my switch over there, and caused that field to collapse, and the energy of that field goes into the spark. In any circuit with inductance, we alternately store and release magnetic energy rapidly in inductors. In astrophysical magnetic fields, energy can be released very quickly by the collapse of these magnetic fields, typically associated with current systems. One place where that occurs in my own research is in the solar corona. And in the solar corona, we have magnetic fields associated with currents that are flowing in that highly conductive atmosphere. If those currents are suddenly interrupted or collapse, that magnetic energy can turn into kinetic energy and result in whole-scale ejections of material from space. In laboratory magnetic fields, we store energy. In a lot of technological devices, we store energy in magnetic fields, and most importantly, we'll get to this in Lecture 40, in electromagnetic waves, this energy is available for release. You see at the bottom right here the results of one of these superconducting quenches where magnetic energy was released unexpectedly and explosively too quickly. Magnetic energy is truly universal. Now, in every other lecture, I've ended with a summary. In this lecture, I'm not going to give you a summary. Instead, I'm going to give you a comparison, a side-by-side comparison, because what we're getting at in this intermix of very practical things like how solenoids work and car starters and so on, and this much more profound issue of magnetic energy, we're approaching this convergence of electricity and magnetism into this one unified field of electromagnetism, which is going to come to complete fruition in Lecture 40. So let's look instead of a summary, at a complementarity, as we understand it so far, between electricity and magnetism. Let's look at the electricity case first. In the electricity case, we have parallel plate capacitors. They create uniform electric fields. There is stored energy. U is a half CV squared, as we found inside a capacitor. Where is it stored? It's stored in the electric field of the capacitor. The voltage across those capacitors can't change instantaneously because it takes time to move charge on and off the plates of the capacitor. And more profoundly, we concluded from looking at the energy stored in a capacitor, that 1/2 CV squared stored in a parallel plate capacitor, a simple configuration whose capacitance we could calculate, we got the energy density stored in all electric fields. And again, it has the form 1/2 times a constant involving the electric constant. In this case, the constant is 1 over 4 pi k, then times the strength of the electric field squared. Now, this is a complementarity. Let's look at magnetism. We've got long solenoids. A solenoid looks nothing like a parallel plate capacitor. It doesn't work on anything like the same principles. But it is complementary analogous. It's the magnetic analog because it creates a uniform magnetic field. It has stored energy 1/2 Li squared, the inductance L playing the role of capacitance C, the current I playing the role of voltage V, and the current, as we saw, can't change instantaneously. And if you try to make it change instantaneously, as we've seen, you can have disastrous results. And finally, we reach the profound conclusion that there is energy density in magnetic fields, and it is 1/2 times a constant, this time the magnetic constant, or 1 over it, times the strength of the field squared. So there is this complete complementarity between electricity and magnetism, and these mundane practical devices, capacitors and inductors, have helped us to see this profound complementarity and almost equality or analogy between electricity and magnetism that pervades through the entire universe and gives electric and magnetic fields one of the most important quantities in physics, and that is energy.